Good morning, students. Now we have completed up to the chapter of magnetism, right? Today we want to discuss the next chapter. We are starting the next chapter, that is electromagnetic induction. Obviously, after finishing electromagnetic induction, we have another chapter of AC also with it. So electromagnetic induction. So we are going to discuss today the electromagnetic induction. We are starting this chapter of electromagnetic induction with this magnetic flux, a very important term that is called magnetic flux. Magnetic flux is very much similar. Its definition is also very much similar to the electric flux, which we have discussed already in our electrostatics chapter. Alright, so let us first see what is a magnetic flux. Magnetic flux through any surface placed in the magnetic field. Okay, magnetic flux through any surface placed in the magnetic field is the total number of lines of force crossing this surface normally. That means, what is magnetic flux? It is indicating the total number of magnetic lines of force which are crossing normally that surface. Which surface? The surface which is placed in the magnetic field. Alright, it is like this. This is called the magnetic flux. Okay, now let us suppose there is a surface. Here is the surface having the area capital A. Let us consider this surface having the area capital A. Obviously, A vector will be perpendicularly outward. This is outward normal, right? Along this, A vector will be acting, and B vector, it is placed in the uniform magnetic field. I told you, uniform field means the direction and magnitude of the field will remain the same in that particular region. So, in this region, B vector is acting in such a way that its direction is forming an angle theta with the direction of A vector. Like this. In that case, what will happen? What will happen? The magnetic flux phi B. B stands for magnetic, because there is the electric flux also. So phi B, that should be equal to B vector dot A vector is equal to B into A into cos theta. So magnetic flux is defined as this. Just like I told you, it is parallel to the electric flux. B vector dot A vector is equal to B into A into cos theta. That means, can we say the three cases? There may be for theta equal to 0 degree, cos theta equal to 1, so phi B must be B into A. Then, second, for theta equal to 90 degree, cos theta equal to 0, so phi B must be 0. And C, for theta equal to pi, cos theta equal to minus 1, so phi B should be minus B into A. Look at this. Look at these three cases. Phi B is equal to 0. Oh, sorry, I think the last line may not be visible, so just a minute. If the last line is not visible to you, here I write phi B is equal to 0, it's alright. Now we are coming here, the C part. I write here for theta equal to pi, okay, cos theta equal to minus 1, and phi B should be minus B into A. I think now it's very clear. All the three cases are completely visible. You can see. Alright. And since you know dot product is always a scalar quantity, so this value will be the maximum value and this value should be the minimum value. As far as flux is concerned, it is this. once you go through, children, all of you just go through it. I think it is all right. I have defined magnetic flux and all the things here. If you say unit of flux, magnetic flux, definitely you know it is Tesla meter square. I hope I have told you in the previous chapter the unit for magnetic field intensity in the SI unit, that is Tesla. Okay, Tesla into meter square. Tesla into meter square, that is actually called, you know, it is known as Weber. W-E-B-E-R, Weber, and it is Weber. It is written as W-B, like this. It is called Weber. Tesla meter square. I think again it is not visible, sorry. Unit of flux, I write here. Unit of flux, Tesla meter square, which is called Weber, that is WB. Look at this. Tesla meter square, that is Weber. This is all about our magnetic flux. I hope you understand what I have said regarding the magnetic flux. I have started this chapter of electromagnetic induction. I am doing this chapter of electromagnetic induction and I have started it with magnetic flux. This is all about magnetic flux. Now we are coming to our actual topic, that is, I have written here again, you look, it is EMI. It is the short form of electromagnetic induction. Electromagnetic induction, the short form of electromagnetic induction is EMI. What is EMI? Electromagnetic induction. Actually, I tell you, electromagnetic induction, this phenomenon was Michael Faraday has invented this. Michael Faraday was the physicist who has discovered this. And what is electromagnetic induction? You can write. You can write the definition. It is the phenomenon of production of. It is the phenomenon of production of induced current. It is the phenomenon of production. It is the phenomenon of production of induced current and hence induced EMF. Induced current and hence the induced EMF due to the change of the flux through a closed coil or the closed circuit. Due to the change in the flux in the closed coil or the closed circuit. I repeat, it is the phenomenon of production of the induced current and hence induced EMF due to the change in the flux through a closed circuit or a closed coil. Now let us see what does it mean. Look, I have drawn here these three figures. Just focus on these three figures. You just concentrate on these three figures. What we are getting? There is a coil. There is a coil. The orientation of the coil is perpendicular to the field, perpendicular to the board. Perpendicular to the board, like this. Right. It is perpendicular to the board. Here, like this. Just see, my palm. This palm is actually the orientation of this coil, closed coil, like or closed loop, and it is connected to a galvanometer. What is this? It's a galvanometer. You just see. There is no cell in this circuit, only the galvanometer. Here is the galvanometer. Okay, so it's placed like this, and what happens? There is like this. This is, you see, this marker as the magnet. Its north pole is here. Look, north pole is moving towards the coil. If the north pole is moving towards the coil, just see. I hope All of you got it? Got this point? It is placed like this, and this is moving towards the coil. What happens? We see, look, there's an anti-clockwise current flowing. Could you observe? The anti-clockwise current is flowing. Look, anti-clockwise current is flowing. I hope you got it. That means, what I am saying repeatedly, there is no cell. Till now, we have studied that there must be a cell which will deliver the current. But here there is no cell. Still, what we are getting? Like this, the magnet is moving, current is flowing, anti-clockwise. Galvanometer is showing the deflection. If the magnet is moved away, here, the direction of the current changes. Look. Okay? The similar phenomenon can be observed in case, look, I write here, this phenomenon, this anti-clockwise current will be seen if the south pole moves away, understand, opposite, north pole towards, and south pole, if the south pole is moving away, the similar direction. And here, south pole moves towards. Look, if the south pole moves towards, it will give the same direction as the north pole is moving away. And if either north pole or south pole is static, coil is also static, this is also static, then what happens? No current. This is the observation. Just focus, look at these three figures. Look at these three figures, what I am getting. Okay? In the next lecture, just now, I am coming to the mechanism, why it is happening. I hope you have understood these observations. Now we are coming to why it is happening in that case. Right?